right? Yeah, let's see. We had to go to we went to a funeral. A gentleman in our church passed away, so that was sad. But otherwise it was on a weekend. Do you have any news? No? Morning. I'm going to hand back your exams at the end of class. I do want to go over just sort of our schedule because I think that maybe when I made out the syllabus that I intended the final to be cumulative, but I would rather not have the final be cumulative, right? In fact, what? But in order to do that, no, it's not April Fool's. What? Short? Am I sure? Yes, I'm positive. Like, I mean, I don't even talk about a final in the thing. What's this called? A syllabus? So this exam 4 just counts 100 points, just like all the other exams. And I want it to just cover a chapter. That chapter will either be electric properties or optics of the eye. I'm not sure which. And then the next exam will cover sound, speech, and hearing. But that means that we're going to have to change things just a little bit with the schedule. So that exam won't be on Tuesday, May 1st. Y'all are going to love this. Instead, that exam will be on Thursday, April 17th. It's right before spring break, I understand, but that's good. So then you take the exam and then you're done. You go off spring break and do whatever it is that you do on spring break. Okay? Right. Uh-huh. And we'll be done with it by then. Maybe even having moved on part of a class to the next chapter. But it will just be this sound chapter. Otherwise, we only get like a day and a half or whatever to cover the next chapter, and that doesn't really make any sense. Okay, so I'm sorry for that change, but you might want to mark that on your syllabus that instead of Tuesday, May 1st, this is going to now be Thursday, was it March 20, April 27th? April 17th. And exam 4 is the final, but not cumulative. It's just a normal exam, okay? And it'll be either on electricity or on optics. I'm not sure. I'll have to take a look and see, I don't know, which I like better. Huh? Right, the university sets that date. So, all right? Okay. Let me read. She asked about the chapter review. Select chapter in the book, on which write a chapter review, 1,000 words or more. Summarize the chapter. It needs, yeah, it needs to summarize the chapter. Okay? Is that clear? But then you can pick a subtopic, like if you need additional length. I would like for you to pick a topic within the chapter and then, elaborate on it. Destiny? It needs to be 5 to 7 minutes. Cover, isn't that what I say here? You also need to let me know beforehand. That is the chapter review. How many of y'all are going to do the actual presentation, are you thinking? Okay, for the chapter review, you can either write 1,000 words or you can do a 5 to 7 minute presentation. How many would do the presentation? 3, 4, 5? Okay, y'all need to shoot me an email this week, okay, and tell me that you intend to do that. All right, let me make a note to myself so I can remind y'all. Oh, it's going to be, yeah, like the last day of class or so. Like we'll take some time in class to do that. Or depending on how many of you do it, I might do something else. But yes, last day of class. And hey guys, hey guys. And yeah, so that chapter review is due by the last day of class, let's say. I don't think I have a due date here. Do I? Our last day of class is May 6th. Okay? May 6th. All right, so let me get this on my calendar, April 17th. That's exam 3. Okay. Any questions? We're getting close to the end here, so we're getting close to the end. So one more exam and then that final. Guys, Hannah, what? She answered your question? Okay. I also want to do a reading quiz for this chapter on sound. Today's Tuesday. We won't do it on Thursday, but we'll do it next Tuesday. Yeah, next Tuesday, that is going to be the 8th. Okay? Ah, shoot. This Thursday? Yeah, listen, let's do it this Thursday. We'll do it just on the first half of the chapter, though, up to... Guys, this is good for y'all because if we get... I'd like to get in maybe 2 more quizzes, but remember, I only keep the top 4, and we're already up to 4. I'd keep the top 4, yeah. That's what it says on this. We'll go up to page... hey, guys. Yes? We'll go up to page 121. That's the anatomy and physiology of hearing. Up to that point. Or no, I'm sorry. No. Up to page 116. That's the anatomy and physiology of speech production. This Thursday, yeah. All right. All right, guys, you got all that? So next exam, April 17th. Reading quiz, April 3rd. And the final exam is as scheduled. If the paper and our presentation that you're doing is due on the last day of class, which was May, what do we say? 6th, May 6th. And there is no class on April 8th. I'll be out of town. Any questions? All right. Let me make a note. So, exam moved. Reading quiz. What page number did I say the quiz is through? Through what? Page 116. All right. All right, we're moving on to sound now. This is kind of a fun chapter. We'll talk about waves and what waves are and what defines waves, some of the basic properties of waves, velocity, frequency, amplitude, period, those sorts of things. Some of this you might have seen before in high school physical science or maybe in, I don't know, where else you might have seen that, waves. But then we'll also get into production of sounds, different types of waves, transverse, longitudinal, compressional waves, sound waves, and then how we produce sound and some of the properties of that, and then also how we detect sound, both with microphones and with the human ear. So we have lots of different examples of waves in the world. There are many examples of waves. We have waves in water. Like if you're out on the lake, you'll see waves on the surface of the lake or in the river or whatever. We have sound waves. So right now, as you hear sounds in the class, the rustling of paper or me speaking or whatever, that's because of waves that are traveling through the air between the source of the sound and you. They're actually compressions and then rarefactions of the air, areas of low and high pressure that impinge upon your eardrum and actually cause you to detect this sound. If we get to it, I'm not sure if we'll get to this chapter, but light is also described as a wave. It's a special kind of wave called an electromagnetic wave, and it's different in a lot of ways from sound waves, but it's also similar in a lot of ways. And so the ideas of frequency and wavelength and period and all that jazz will apply to light as well. You can have a wave in a slinky. Let's see, I think I have a slinky. Yeah, so you can have a couple different kinds of waves in a slinky. Like I can have a wave where I make it travel along the slinky, like that. Let's see if I can do it again. You'll see how a wave moves up and down the slinky. But then that's called a compressional wave or a longitudinal wave. But then I can also have a wave like this, and that's called a transverse wave. I'll define those in just a bit. The difference between a transverse and a longitudinal wave, by the way, is how the medium moves. In a transverse wave, the medium moves up and down, but in a compressional wave, it moves back and forth. I'll write that in just a bit. All right, so you can have a slinky wave, you can have a rope. Morning, ladies. Waves are periodic. That means that they repeat. In fact, they're called periodic waves. That's what your book calls them, periodic waves. Now, a standing wave you've experienced before. This wave travels back and forth in a medium. Travels back and forth in a medium and repeats, so it looks like the wave isn't moving. You ever do this exercise where you get a big rope and you shake it up and down? You or your athletes, you know the exercise where you take this big rope, like big old rope, and you move it up and down. Well, that's a standing wave. See, I have one, and it looks like it's not moving. Tiffany, am I holding this for me? Just hold the end. All right. So with this, you can move the rope back and forth, and you set up well, that's just jiggling back and forth. I want to move it up and down. You just don't move at all. Okay, well, that's fine. Well, this is a standing wave too, actually, right? That I have this wave that's actually moving across. What I'm trying to get here is an up and down motion. Just hold your hand steady. Right? So this is, there we go. That's a standing wave. And it looks like the wave isn't moving because I have these set points in the wave. You can just drop it. Thank you. So in a standing wave, like for example, in a string, or you can have it, I'd have two, or you can have it in sound as well. I have two fixed points, and then I can have it look like that, although they'd all be equal. And so that's a standing wave. But the wave is moving back and forth in such a way so that you have these points here. We call these points nodes. You don't need to write that down, but they're called nodes. And it just repeats back and forth. There are only particular conditions where you get these standing waves, but it just repeats back and forth. In sound, we would call this resonance. We're not going to get into resonance here, but if you have a tube, there's a particular frequency or a particular type of wave that will resonate within that tube. And it makes a tone and can actually get very loud. One time when I was in high school, I went to a boarding school, and we got a frequency generator and a speaker, just something that generates a tone of an even frequency, unlike music, which is a lot of different frequencies or pitches. And we figured out what was the resonance frequency of the stairwell. And it was really cool because you could have your speaker operating at this resonant frequency, and the whole building just started to vibrate because we found this resonant frequency of the building, basically. And we set up this standing wave. All right. Sound waves are periodic, just like all waves. Sound waves are periodic. A sound from a guitar is periodic. Or any musical tone is periodic. That means that that wave is going to repeat over and over again. Even though you might not think of this, that this wave is actually repeating over and over and over again, it actually is. Anybody play musical instrument, guitar or whatever? Yeah? What do you play, Caleb? Piano? Okay. Well, anyway, a sound from a guitar is periodic. Um, a clapping sound is also periodic, your book points out. It's also periodic, albeit very short. And so we don't really think of it as repeating itself because a clapping sound, when I do that, is a periodic sound, a periodic wave, but it's just very short. And so we don't think of it as repeating itself. Um, what is it? Albeit? It's like although. It's sort of like although, yeah. It's like the fancy way to say although, I guess. Like what Fancy Nancy would say. That's fine. All right. Sound waves, or waves in general, always have a medium. With the exception of light, which if we get into that light chapter, we'll talk about how light doesn't have a medium to travel through. But as far as we're concerned, waves will always have a medium. So for example, like with the wave on the rope, your medium is what? The rope. With sound waves, the medium is the air in the room. In fact, if you took all the air out of the room, I mean, that would be a problem for us, of course, but if you took all the air out of the room, you wouldn't hear any sound. And so you don't hear sound in space, for example, because there's no air, no medium for which to travel through. So waves always have a medium, uh, and the waves will cause the medium to move in a particular way. I'll show you an example of this in just a bit. The waves will cause the medium to move. So you can think of these waves as a disturbance in the medium. Right? I can make a disturbance in the medium just by moving my hand back and forth, right? And that causes the medium to be disturbed. But when you have a wave moving through a medium, you change the medium in a very regular way. Again, I'll show you a video in just a couple minutes that illustrates this. All right. Let's define transverse versus longitudinal waves. Transverse and longitudinal waves are different in the way that they change the medium. All right. Y'all ever done the wave, like at a sporting event or whatever? Like if we did the wave here, I'm not going to make y'all do that, but this row would stand up first, and then as they were sitting down, this row would stand up, and then this row, and then on and on. Right? Y'all know the wave, right? Okay, what type of wave would that be? I've already named the two types, Fiona. That's a transverse wave. A transverse wave causes the medium to move up and down. Now, if y'all were a wave, what would the medium be? No, you would be the medium, right? Because you're the thing that's moving up and down. And so row one would stand up, and then they'd sit down, row two, blah, blah, blah. So the wave, like you would see at a sporting event, put it in quotation marks because it's like, a sporting event wave, is a transverse wave. It causes the medium to move up and down. Now, a longitudinal wave, on the other hand, a longitudinal causes the medium to move back and forth. A longitudinal wave causes the medium to move back and forth. So if we were going to do, instead of a transverse wave, like at a sporting event, we instead wanted to do a longitudinal wave, I don't think this would look nearly as cool. Yeah, you would, instead of jumping up and down, you would like compress together, and then you'd move apart, and then this part would compress together, and then you move apart, and then this part would compress together, and then you move apart, and then this part of the room would compress together. That's not nearly as impressive. Although I think if you got like, 50,000 people to do it, it could look really cool. But so that would be a longitudinal, which we'll also call a compressional wave in just a bit. Yeah, that's a type of wave. She's talking about the Newton's cradle where you have, y'all might have seen this, or you have one ball that comes down and then they knock one another and then the other one comes up in the end. So that's a type of wave that travels through the steel balls. We'll talk about that. It's a vibration of sorts. All right? So longitudinal wave. And by the way, a longitudinal wave, this is going to be a sound wave. Because sound causes the medium not to move up and down, but the medium to move back and forth as we have pressure variations within the medium. All right, I want to show a video. This is, you might not see that it's immediately relevant to waves, but it actually is quite a bit, because waves have a certain velocity, and when something like a slinky drops, you can think of it as a wave traveling from one point to another. So in this video, they're going to deal with a slinky drop. Have you ever seen this video? Let me stand up so y'all can see. It's actually really cool. When you have a slinky that drops, there are several different things that could possibly happen. Like if I have a slinky from up here, and then I drop it, how do you think it's going to drop? Or what's going to happen to the bottom part when I let go up here? Will it go up? Will it go down? Or will it stay where it is? What do y'all think? Let's try it, okay? So let me let this out a little bit more. It happens quickly, okay? So you have to watch closely. I'm about to let go. I'll count down to 3. 1, 2, 3. It stays exactly where it is. Now you can think of this as a wave because when I let go of the top here, then I'm allowing this compression to occur. And it gradually compresses more and more as it goes down. And it moves at a certain velocity as it moves through. And so that's the point I want to show as we watch this, that you think about this wave traveling through the slinky, through the medium of the slinky. We think of this, people in astronomy, we talk about this as, we would say that the bottom of the slinky has not yet received the information that the thing is falling yet. Because the information travels along here. The information, I mean, slinkies don't think, right? But it hasn't yet found out that it's supposed to be falling yet, because the information traveling down the slinky at the speed of the wave hasn't reached it yet. And so as you let it go, this guy is just dumb until this part gets down to the bottom and says, oh, you're supposed to be falling. So let's watch again. Let's have a little video. This is from the Veritasium channel. Actually, I think this was on ABC or something, this little clip. It's just a few minutes. So let's watch. All right. All right, so let's define some things about this type of motion. We call this type of motion, by the way, simple harmonic motion. Simple harmonic motion. I just want to define some things about waves. Some of this you're probably familiar with. First of all, the equilibrium position. This is sort of like the position at rest. So let's say that I have a certain type of wave would be like a mass on a spring. So say if I had a mass on a spring, then I can make it oscillate back and forth, just like a wave. If I pull on it, it can oscillate back and forth. And the equilibrium position is just going to be where it is at rest, right this. Right? The equilibrium position in terms of a sound wave would just be the normal pressure of your room, right? Whatever the air pressure is. And then the sound wave is actually going to cause higher pressures and lower pressures than that. Right? So the equilibrium position is a position of rest. Like if I have a spring with a mass on it, it is where I would call x equals 0, and then it would move in this direction, and it would move in this direction, moving from that equilibrium position. For sound, the equilibrium position is more of a pressure. It's the we'll call it the ambient pressure of the medium. So in this room, there is a certain air pressure, 1 atmosphere about, give or take a little bit. All right, but as you speak, you cause that pressure to be a little bit higher and a little bit lower, but it oscillates around this equilibrium position, which is the pressure of the air in the room. All right, so that's equilibrium position. The amplitude is how much it deviates from the equilibrium position, how much the medium deviates from the equilibrium position. We'll call it EQBM for short. On a wave, we often draw them like this. This would be for like a transverse wave, for example, where I would make a plot of, we'll call this time, I'll call this position, I'll call it x, and we would draw a wave like this. Right? The equilibrium position would be here at x equals 0, and then the amplitude would be the distance from here to here. So this would be the amplitude. Now for a sound wave, you can make a similar plot, but instead of plotting position of the wave, you could plot the pressure of the atmosphere, and it would look the same as this. The pressure would be big at some points. It would be equal to whatever your ambient pressure is, and then it would be small at other points. All right? So we'll use this form to describe a wave, and the amplitude is just the distance from the equilibrium position, or the origin, up to the peak. Or you could draw it like this as well. This is also the amplitude. Because it repeats, the amplitude is the same in either way. The period is the time for one complete oscillation. So if I have a wave, one oscillation is going to be starting at this point and then coming back to the same point. So the time for that one complete oscillation is called the period. The time for one complete oscillation. The point being here that I start at one position and end at the other. All right, now if I were looking at the period, say on this plot, it would be beginning here and going not to this point, but over to this point, coming back to exactly the point that I started. So if I have my mass on a spring, this is simple harmonic motion. It's like a wave. One complete oscillation would be the distance from here to here. One oscillation, two oscillations, 3, 4, one complete cycle of motion for a wave. And that's going to be the period. The frequency of the period we'll call T, capital T, and it has units, of course, of seconds. The frequency, which you've probably heard, and we'll deal a lot with frequency because frequency is related to the pitch of sound, is related to that period. Can I go down from here? Okay, the frequency, you can write it as an F. Usually you'll see it as a script F like this. The frequency is just the inverse of the period. And it just says how many points in a given time, how many crests of a wave pass in a given amount of time. Right, so the frequency is 1 over the period. We measure this in hertz. The unit for frequency is the hertz. It's after a physicist from the 1900s, Heinrich Hertz, and it's abbreviated HZ. 1 hertz is the equivalent of 1 inverse second, or you can think of it as 1 over seconds. All right, so it's just the inverse of seconds, and you can see that from the equation here. So the frequency is 1 over the period. Now for sound waves, we'll see this again in a little bit, but let's go ahead and write it down here. That for sound waves, the loudness of your sound is proportional to which of these quantities? Now I've listed several quantities. I've listed the amplitude, the frequency, and the period. Which is the loudness of a sound proportional to? The what? Not the frequency. The amplitude, yeah. So the amplitude is proportional to the loudness for sounds. All right? And then the pitch is proportional to the frequency, or inversely proportional to the period. But usually when we talk about sound, we don't talk about the period of the sound, we just talk about the frequency. Is that correctly? Yeah. So the pitch is proportional to the frequency. So you can have high pitches, or you can have low pitches. High, low. Can y'all do that? Like, that's my little trick. Try it, it's not that easy. High, low, high, low. Okay. Okay, all right. You can try it later, and you can practice, like in your bathroom in front of the mirror, and then you can impress your friends right after you show them the slinky thing. It throws my kids off, they like it. Okay. One other thing, and that is the velocity of a wave. Remember with the slinky, the wave actually traveled through the slinky at a particular velocity. The velocity is equal to the frequency times the wavelength. The velocity of a wave is given by the frequency times the wavelength. If you ever forget this relationship, just think about the units. Because frequency, oh, I'm sorry, I didn't do wavelength. Okay, we'll come a step to the side here. Wavelength. Remember the period was the time for one complete oscillation? The wavelength, which we call lambda, is the distance for one complete oscillation. All right, I can make a plot of a wave that looks like this. I'm going to change the axes here, but don't sweat it. But the wavelength is the distance from here to here for one complete oscillation. That's one wavelength. Likewise, the wavelength, if I was measuring it from this point, it would go from here over to here. You see how those are the same distances. It's the distance from one point after a full oscillation of my wave to the next point. That's wavelength. And then the wavelength and the frequency are related by the velocity. And so returning to this, sorry, I sort of jumped the gun. So the velocity of a wave is equal to the product of the frequency and the wavelength. But if you forget this, the units for frequency are 1 over seconds, and the units for wavelength are meters. And the units for V, of course, are meters per second. Right, you might look at that and think, well, if I change the frequency of a wave, like so for example, would you say that high frequency sounds have a large or small velocity from looking at that? If I have a high frequency, that is if F is very big, how would you say V responds? Big or small? It would be big, but that's not true, right? So the frequency does not impact, or the frequency is not correlated or related to the velocity. All right, so high frequency sounds don't necessarily travel at a faster rate than low frequency sounds. All right, they just have a different wavelength. So waves with a very high frequency will have a very short wavelength, and waves with a very low frequency will have a very long wavelength. We'll see a question like this in just a second for a clicker question, but let me just pose it here. Which of these would you say has a higher frequency, the top or bottom? The bottom has a higher frequency, all right? Remember, the frequency is the inverse of the period. Huh? Yeah, let's go. Frequency, think of it, frequent, right, means how many times per second. So here I have more peaks per second than I do up here. So this one has a larger frequency. I'm going to pose you some questions in just a few minutes and we'll readdress this, okay? Which of those has the longer wavelength, by the way? The top or bottom? The top has a longer wavelength. Remember, the wavelength is the distance from peak to peak, this distance, whereas this one has this little bitty distance. So this one has a big frequency, but a small wavelength. This one has a big wavelength, but a small frequency. So frequency and wavelength are inversely related, and they do not correspond to the velocity. All right, so big wavelength, small frequency. Small wavelength, big frequency. Let's see here. Let's do a few questions here. So I've been typing out the questions instead of just writing them, so I brought them. Which of these is a transverse wave? We'll just do about 5 or 6 questions here. Which of these is a transverse wave? A sound wave, a water wave, a compressional wave, a longitudinal wave, or all of these transverse? Which of these is a transverse wave? All right, I'll stop at 1 minute, so you have 5 more seconds. Okay, very good. B is the right answer. A water wave. All these others are longitudinal or compressional waves. A sound wave is a compressional wave or a longitudinal wave. Compressional and longitudinal, those are just, a different type of wave, and it's not E. So B is the right answer. Let's try another one. Hold on just a second. Try reopening this. Okay. If the period increases, what happens to the frequency? Does the frequency increase, decrease, or remain the same? So if I increase the period, remember that was T, what happens to F, the frequency? What? The period. Okay, very good. The frequency and period carry an inverse relationship. Frequency is 1 over the period. I'll stop at 52, 55, let's say. Okay, very good. B is the right answer. The frequency is 1 over period. And so if I increase my period, that decreases my frequency, an inverse relationship. The period of a wave is 2 seconds. What is its frequency? Stop at 45. 45. Very good. C is the right answer. So these are pretty simple, but you can see questions like this on the test. Just need to know the relationship between these frequency, period, wavelength, and velocity. Here, the frequency is just 1 over the period. So that's 1 over 2 seconds, which is 0.5 hertz. Right. The loudness of a sound is given by which of these, of the wave? The frequency, amplitude, so the timbre, or the equilibrium position. Timbre, is that right? Timbre? Timbre, right? All right, I'll stop at 35. 35. Excellent, very good. Good job. Yeah, somebody told me one this weekend. How'd it go? Why can you never trust an atom? Because because they make up everything. Thanks a lot, Tori. All right. The loudness of sound is given by the amplitude of the wave. And remember, the pitch is the frequency. Oh, shoot. But y'all knew that anyway. No, atoms. Okay, just a few more seconds. I'll stop at 33. Oh. Okay, the pitch is given by the frequency. That must have been some other class outside of here, right? So you need another one, right? Okay, so a pony walks into a bar and he says, I'm sorry, I don't condone bar jokes, but this is a pretty good one. A pony walks into a bar and he says to the bartender, can I have a drink? And the bartender says, what? And the pony says, can I have a drink? And the bartender says, what? I can't hear you. And then the pony says, sorry, I'm just a little hoarse. I don't get it. Wood? Oh, it's the bartender, like a steak. Yes, I get it now. All right. Let's try this one. The speed of a wave is 10 meters per second, has a frequency of 2 hertz. What is the wavelength? Remember back how, okay, how are velocity, wavelength, and frequency all interrelated to one another? We'll just do a couple more and we'll move on. All right, stop. 110, 110. Okay, A is right. Let me show you. There are several ways you could approach this, and I heard some of y'all talking about it, but the simplest way is probably just to say V equals F lambda. All right, V is 10 meters per second. F is 2 hertz. And so lambda, it has to be 5 meters. All right, 10 divided by 2 is 5. You could find the period. This would be more difficult. But you could find the period, which is 1 over the frequency, so it's a half a second. And then you also know that velocity is distance over time, where this distance would be the wavelength that it travels. And so the velocity would be 10 meters per second equals d over 1/2. And so d would equal 5. That's a bit more complicated to do it that way. But you do need to remember this relationship, that the velocity is equal to the product of the frequency and the wavelength. So I've told you actually that if you change the frequency, that does not change the velocity, right? But that doesn't really seem to flesh out here, right? Because it looks like if I change my frequency, it'll change the velocity. So what is the velocity set by for a particular wave? You might not know this, but I'll entertain a guess. What is the velocity set by? So I've said that neither the frequency nor the wavelength of a wave tell you what its velocity is. All right, if I change the frequency, it does not change the velocity. So how do I change the velocity of a wave? I change the velocity of the wave by changing the medium. All right, we'll talk about that later as we get along. But like for example, in this room, I could change the medium and change the speed at which sound would travel. I could change the temperature of the air, or I could change the type of the air, or the density of the air, and then that would impact the velocity. But changing just the frequency or the wavelength does not change the velocity. Only changing the medium itself changes the velocity. We'll see that in a little bit later. Let's see, I think I have 1 or 2 more questions here. Let's try this one. The velocity of a wave is 10 meters per second. Its period is 2 seconds. What is the wavelength? A couple different ways you can think about this. Remember, the wavelength is the distance that it travels in a period, in a full oscillation, which is the time for the period. All right, we'll stop at, say, 105, 105. 5 more seconds. Okay, A is the right answer. C, what did y'all put C for? Oh, 10 over 2. I got you. Let me show you. Velocity at its basic form is just d over t. The distance that we travel in one period is one wavelength. So I can also say that velocity is the wavelength over the period. But that also fleshes out here when I say that the velocity is equal to the wavelength times the frequency. Remember, frequency is 1 over the period. All right, so it's lambda over t. So you can think about it in either way, but either way is going to get you to this final expression of the wavelength over the time. So 10 meters per second equals the wavelength times the time, over the time, which is 2 seconds. I cross multiply. 10 times 2 is equal to lambda, or 20 meters. All right, so A is the right answer. And one more here, or no, two more, I'm sorry. Which of these shows the wavelength of the transverse wave? Is it A, B, C, or D? Let me show you. A is the distance here. B is the distance here. C is the distance along here. And then D is the distance between these 2 points on this wave. Which of these shows the wavelength? Remember, the wavelength is the distance for one complete oscillation, starting at one point and coming back to that original point. So which of these shows that? A, B, C, or D? Can y'all see that okay in the back? Yep. All right, I'll stop at 112, 112. Okay, most of you put B. B is right. A wavelength starts at one point. Starting here on this wave for all the points, and one full oscillation comes back to there. Oh wait, no, I'm sorry. No, it's not C. I'm sorry, that's wrong. That's wrong. Comes to here. It's not C. That is that's B. That's B. B is the right answer. For one full oscillation. All right, you think about this, like if you notice this point, I'm going up on this wave. Similarly, over here, I'm going up at this position. So if you're in an upgoing position, you'll need to return back to an upgoing position. That's one complete oscillation. One complete oscillation. It's easier if you draw it from peak to peak. So for example, this is also one complete oscillation. That's also one wavelength. But you can transfer that anywhere around on the wave. And one more. Do you like having the questions like this, sort of one after the other? Okay, I'll try to do that more. So which of these waves, these are just waves that I've drawn, which has a higher frequency, A, B, C, D, or E? Which has a higher frequency? Let me remind you that frequency is inversely related to period. Frequency is inversely related to period. So if frequency is big, which is what I'm asking for, which has the higher frequency, the period has to be small. All right? So there's an inverse relationship there. And frequency is also a measure of how many peaks pass a point in a given amount of time. The more peaks that pass a point in a given amount of time, the higher the frequency will be. All right, I'll stop at 135. Okay, A is the right answer. A is the right answer because the peaks here are closer together, all right? So as I have a certain amount of time that passes, I have more peaks that pass in that given amount of time. Or you can think of it that this has a smaller period than any of the others. And so it has a higher frequency because of that inverse relationship. D, I think, D actually has the longest period. It also has the highest amplitude. But amplitude and frequency are not related. Right? I can have a high-pitched sound that has a large amplitude or low amplitude, and it doesn't affect the frequency. Remember, the amplitude only affects the what? The volume or the loudness, yeah. Okay, let's do a couple more things, and then a few minutes before the end of class, I'll give your exams back. Oh, actually, I wanted to show you all a video. This is just a couple minutes long, and it's from the Khan Academy, and this is like for pre-med folks, but just showing a wave and some of the properties of a wave.